Hey everyone, and welcome. Today, we're going to unpack one of the most important rules in all of physics. Seriously, it's a law that explains everything from why a baseball flies through the air to how planets stay in orbit. So yeah, let's jump right into Newton's second law of motion.
So let's start with a super simple question. What does it actually take to make something move? I mean, it seems obvious, right? You push it, and it goes. But have you ever really thought about the connection between how hard you push, how heavy the thing is, and how fast it ends up going? We all kind of feel this out intuitively, but today we're going to see it with the beautiful precision of physics.
And you know what? We don't need a fancy lab for this. All we need is a shopping cart. Let's do a quick thought experiment that I guarantee you've done a million times in real life without even thinking about it. Okay, so picture this. You're at the store with an empty shopping cart. You give it a good shove, the same kind of shove every time, and whoosh, it just takes off, right? It accelerates really fast. Now, same store, same you, but this time the cart is loaded to the brim. You give it that exact same push with the exact same force, and it barely moves. It just kind of creeps forward. Right there, in that moment, you've just perfectly demonstrated Newton's second law. You already know that if the force is the same, more stuff, more mass, means way less acceleration. And what's so cool is that this feeling, this relationship between your push, the cart's heaviness, and how its motion changes, well, physics gives us the perfect language to describe it. It can capture that entire experience in one simple, incredibly powerful formula. And here it is, F equals m times a. That's it. This beautiful little equation is the scientific heart of what we just felt with the shopping cart. The F is your push, the m is the mass of the cart, whether it's empty or full, and the a is how quickly it gets moving, its acceleration. Simple as that. Now, if you look up the official definition, it sounds a little more, well, complicated. It talks about rate of change of momentum. And while that's the full story, the good news is that for most things we deal with every day, things that aren't changing their mass, that big formal statement boils down perfectly to our simple, trusty formula, F equals m times a.
Okay, so we've got this amazing formula. Now let's get our hands dirty and make sure we know exactly what each piece of the puzzle means. Let's decode it so we can really start using it.
First up, we have force, which we measure in newtons. Think of this as the grand total of all the pushes and pulls acting on an object. Then there's mass, measured in kilograms. Now this is important. It's not weight. It's a measure of an object's inertia, which is just a fancy way of saying how much it resists being moved. And finally, acceleration, in meters per second squared. That's just how quickly the object's velocity is changing.
And here's where it all clicks together so perfectly. What even is a newton? Well, it's defined by the other two parts. 1 newton is the exact amount of force you need to take a 1 kilogram object and make it accelerate at 1 meter per second squared. See, it's all connected.
Now, before we put this to work, there are just a few key rules to remember. First, it's all about the net force. That's the sum of everything. If you're pushing, and friction is pushing back, you have to add them up. Second, the acceleration is always in the exact same direction as that net force, no exceptions. And third, this law is instantaneous. It tells you what's happening at any single moment in time.
All right, enough theory. The real magic of a law like this isn't just describing things, it's predicting what's going to happen. So let's take this from an idea to a tool we can actually use.
Okay, here's our challenge. We've got a constant force of 50 newtons pushing on a 10 kilogram object that's just sitting there. The question is, can we predict its future? Can we figure out exactly how fast it'll be going and how far it'll have traveled after 5 seconds? With Newton's second law, the answer is a resounding yes.
And we're going to tackle this with a clear 3-step game plan. First, we'll use F equals m times a to find the missing piece of the puzzle, the acceleration. Once we have that, the rest is easy. We can use some other basic motion equations to find the final speed and then the total distance it traveled.
Okay, step 1, it all starts with our hero, F equals m times a. We just need to flip it around a little bit to solve for acceleration, so a equals F divided by m. We plug in our numbers, 50 newtons divided by 10 kilograms, and boom, we get an acceleration of 5 meters per second squared. That number is the key that unlocks this whole problem.
Now, for step 2, let's find that velocity. We know the final velocity, v, is just the initial velocity u plus acceleration times time. Since our object started from rest, that initial velocity is 0. So it's just 5 times 5, which gives us a final speed of 25 meters per second. Easy.
And for the grand finale, the distance. Using another one of those handy motion equations, we just plug in the numbers we know.
That first part goes to 0 again, so we're left with 1/2 times 5 times 5 squared. A little bit of math, and we find out it traveled exactly 62.5 meters. And just like that, we used a simple law to predict the future.
I mean, how cool is that? But that problem was pretty straightforward, right? The true power, the real beauty of this law is how it works even when things get messy and complicated. This is where it gets really fun.
For example, what happens if you're not pushing something straight on? What if the force is coming in at angle? Well, the law still works, we just have to be a little smarter about it. We have to break that force down into vectors. How much of the push is going forward and how much is going sideways to figure out the object's true path.
Or how about this one? Think about a car engine. An engine provides constant power, but that doesn't mean it provides constant force. Actually, as the car speeds up, the force from the engine changes. This is where F equals m times a becomes the tool that connects force to bigger ideas like energy and power, letting us model things that are much more realistic. And sometimes, physics gets a little sneaky. You might not be given the force or the acceleration at all. Maybe all you have is an equation for where the object is at any given time. This is where Newton's law partners up with calculus. We can actually use calculus to work backward from the position to find the acceleration, and then use our law to figure out the force that must be causing that motion.
And that right there, that's the ultimate takeaway. This law is the fundamental link between two huge fields of physics. You have kinematics, which is the how, it just describes motion. And then you have dynamics, which is the why. And F equals m times a, that's the bridge that connects the how to the why. It's the reason things move the way they do.
And the scope of this one little law, it's just mind-blowing. It's the same simple relationship that governs our shopping cart, that allows engineers to calculate the exact thrust needed to launch a massive rocket into space, and that helps astrophysicists map out the dance of planets around a star. From the mundane to the cosmic, it's the same rule.
And that kind of leaves you with a pretty amazing thought. The elegance of F equals m times a shows us that the universe, for all its complexity, can often be explained by these beautiful, simple rules. So it makes you wonder, doesn't it? If this one law can explain so much, what's the next F equals m times a out there, just waiting for us to find it?